For problem number 12, we've got this metallic bar right here, which is free to move. And then we've got a U-shaped metal wire that when you have the bar attached to it, it creates a loop. So it states here that the bar is dropped from an initial height h above the bottom side of the loop. We want to find the direction of the induced current in the loop. As this bar falls, our flux decreases because there's less area. So to counteract that decreasing flux, we want to add to the flux that's coming out of the board. And therefore, we need a current going counterclockwise to create a flux coming out of the board. So for part A, we would have counterclockwise. Derive an expression for the induced current as a function of speed. So I'm going to do part B right here. We know current is EMF over R, and EMF is equal to negative d flux over dt. In this scenario, our magnetic field is constant, but the area is changing. And so our negative d flux over dt is equal to negative b dot dA and over dt. And there's only one part of the area changing, which is the height. So it's going to be negative b, length stays the same, and the height is dh dt. What we know and have seen quite a bit is that when we've got a change in distance over change in time, that's velocity. And so our EMF is going to be negative BLV over, or rather our current is negative BLV over R. So in this scenario, the negative represents the fact that it's going counterclockwise, so we can just use the absolute value of that, and this would be our equation for part B. The next part is to determine the terminal speed of the bar. So what I'm going to do here is when we have terminal velocity, that means that we've got a gravitational force and a magnetic force equal and opposite. And we can check that. We can see that our current is going to the left. We've got a magnetic field coming out of the page, and therefore my magnetic force is going to point upward. So you want to make sure that that matches what you would expect it to. And for C here, we are going to determine the terminal speed of the bar when they're equal, which means that my magnetic force is equal to my force of gravity, and I'm just going to plug in the equation for my magnetic force here, which is equal to ILB. So what I do have is my equation for current. So again, I'm just going to take the absolute value of that. My current is BLV over R times LB. That gives me mg is equal to B squared L squared V over resistance R. And if I'm solving for velocity, velocity is equal to mgr. Sorry, that should be resistance R over B squared L squared. Okay, so for problem number 12, D, we're going to derive an expression for speed as a function of time when the bar is released to the time when it reaches terminal velocity. So the first thing we need to state is that the initial velocity is 0 because it's starting from rest and then it's released. The final velocity, since we're trying to find the expression as expression for speed, we're going to leave it some arbitrary value, variable v, and knowing that that's going to be the equation for the velocity up to the point where it reaches terminal velocity. Obviously, we have an acceleration because it's not going at constant speed yet, so that's going to be my change in velocity over change in time, and by us setting up acceleration as dv dt, we can get an equation with respect to expression of speed with respect to time. So the first thing we're going to do is we're going to take the sum of the forces equals ma. And it doesn't really matter what direction you choose to be, positive or negative. Generally down would be the negative, but to match the answer key, I'm going to keep my magnetic force with a negative BLV, so that's going to be my negative variable, and then force of gravity is going to be my positive force. So that's going to be mg minus ILB, which if we substitute I, we've got a force, magnetic force of B squared L squared V over R. That's equal to M dV dt, because that's our expression for acceleration. And then we need to bring our values together so that my variable V is with dV, and then I can take everything else to the other side. So what I'm going to do is I'm going to get common denominators. I'm going to divide the top and bottom, or multiply the top and bottom by R to get a common denominator. And then I'm going to take m dt and bring that to the other side. So this whole expression is going to be multiplied to the right, and then m dt, I'm going to multiply the reciprocal to the left. So I end up with dt over m is equal to r, that's my common denominator, over rmg minus b squared L squared v dv. And that's how we can get all our variables together. Then we integrate. This one's going to from 0 to some arbitrary time t. This one's going to go from initial velocity of 0 to some arbitrary velocity, which is what our expression is going to equal, of v. And then because we have this very complex denominator, that's when we get into u substitution. So first, let me complete the left side. Integration of dt, m is just a constant, is going to be t over m. And then for my u substitution, I'm going to get u is equal to the denominator, rmg minus b squared L squared v. And that means that when I take the derivative du, I get negative b squared L squared dv. And I'm going to have to substitute this in there. So I'm going to solve for dv. That's du over negative b squared L squared. And then when we plug in our limits, I need to figure out if I'm starting at v is equal to 0, then u is equal to, plug in v equals 0 here, rmg. And when v is equal to v, I get the exact same expression for u, which is rmg plus, or sorry, minus BLV, b squared L squared v. So let's start with plugging in our substitutions. So first thing I'm going to do is I am going to take my integration, and I'm going to go from rmg to rmg minus b squared L squared v. And then I'm going to take my denominator. So r stays the same. My denominator is now u. And then my dv is substituted in with du over negative b squared L squared. And then from there, I can pull out all my my constants. So I've got r over negative b squared L squared. Integrating, I'm not going to write the limits, I'll just add it in later, 1 over u du, and then that gives me t over m is equal to negative r over b squared L squared ln, And then from there, I'm going to plug in my limits. Instead of subtracting, I'm just going to go ahead and divide. RMG minus B squared L squared V all over RMG. And then I want to get rid of this ln, so I'm going to multiply by the reciprocal of this constant, b squared L squared T over m r, or negative Rm, is equal to ln of this RMG top and bottom. I'm just going to call that 1, and then negative b squared L squared V over RMG. And from there, we can take e of both sides, get rid of that ln. So now I've got e to the negative power. What I want to isolate is this v right here. So what I'm going to do is I'm going to take this, add that to the other side, subtract this e to the right side, and I get b squared L squared V over RMG is equal to 1 minus, 1 minus e to the negative b squared L squared T over Rm. And then all I have to do is to isolate v is multiply by the reciprocal of this constant. And I know it's ugly, but it is supposed to be ugly. I've got RMG over b squared L squared V times 1 minus e to the negative b squared L squared T all over Rm. And, oh, I included the v when I was supposed to isolate it. So that should just be a denominator of b squared L squared. And then everything else looks good. So this is your answer to D. Again, a little complicated math, but not necessarily too difficult of physics.